Great honor to be recognized for this, and it's a great honor to join the 36 other people in this campus that have gotten this award. Mark talked about our land-grant mission, and I'd like to follow up on a bit. So my particular appointment is 55% research, but really when I tell people what we do, it's teaching. Everything we do is teaching. That 55% research is teaching students outside of the classroom. Our core part of our mission that's teaching is in the classroom, and the research part is out of the classroom. And extension is teaching. It's teaching the people that aren't on campus in the state. That makes our university unique in this state. And for those of you who don't know, there is one and only one land-grant school in each of the 50 states. So we're unique in that regard, and we have that extension mission. We're in the library. Those of us who are more senior spent our lives in libraries. And the young people, there are lots of young people here, the library is their computer screen. But Brad Cole is here, the dean of the libraries. All that stuff that happens on your computer screen is free because of the library and the funding for the library. So it's great to be back here in person in the library, because the libraries are the central focus of all universities. Minutes ago, our ambassadors were bringing parents and young students through here, prospective students for our campus. And where do they take them? They take them to the library. This place is full of students here studying. So it's great to have this central focus on the library. I'm going to talk about our stuff with NASA a little bit, but it occurred to me one day, I just love college campuses, and I'm so honored to be able to, I don't know how many I've been on, maybe 50, giving talks at schools, and I always get out and walk around campus, because to me it's just a really edifying environment, every single college campus. So if you're from Mars or somewhere farther away and you're studying the planet Earth, some kind of imaging system, all of those universities would be like petri dishes. I thought this is what they would conclude. Well, look, they have a petri dish here and here. They're little incubators for young talent. And that's exactly what all universities do. I looked up this morning, people that got Nobel Prizes. There's been 911 Nobel Prizes of physics, chemistry, and physiology and medicine. Virtually every single one of those went to a person at a university doing research. There's a few with private industry and a few with national labs that are close to universities, but that says something about where the research is being done, that these people are being awarded. So I'm also proud to be at a campus that a few years ago honored an artist as the Researcher of the Year. That says something about our breadth at our university. And I'm proud that this year, Joanne is only, I think, the third woman to get this award. And I'm proud to be a part of the campus that recognizes that diversity. Aristotle, one of my favorite quotes, said, "Teaching is the highest form of understanding." That's what we do, that's our mission, and we understand things more deeply when we teach them. So, in a few minutes here, I'm going to attempt to show you what we've done with NASA and how it relates to stuff in the planet Earth. Mark, one of the things that's been wonderful having you here is the focus on science communication. We had a workshop last fall. That's teaching. That's figuring out how to explain our science to everybody. So this is my opportunity to try and do a little science teaching here in an engaging way. I'm going to use the movie The Martian as a focus of this, and I'm guessing maybe at least half of you have seen this. I'm going to show you a clip from a trailer from The Martian. So if you haven't seen it, you get the idea. And if you have seen it, you'll be reminded of the focus. So let's take a look at this clip. This is 40 seconds long, And it's one of the trailers for this movie. This is the book that it's based on. A few years ago, it's a great story about how this book got written. It's an online book, and publishers turned it down. People loved the book, and finally then it became a book and a movie. The movie follows the book exactly. This is full of his calculations. And that line, I'm going to science the shit out of this, that's on bumper stickers and T-shirts, and what a great line. I mean, yes. So how are we going to do this? Now he got stranded and he had to make do with what he had, but how about when we go and we're not stranded and we do this on purpose? Let me give you an analogy of how hard it is to go to Mars, for starters. We go back and forth to the space station, and we have been to the moon. By a distance analogy, going back and forth to the space station is like going back and forth to downtown Logan from campus. Going to the moon is like going to the Salt Lake Airport. Going to Mars is like going to Antarctica. That's how hard it is to go to Mars. We're not going to bring all of our stuff with us. We can't. We have to use the resources that are on Mars to do this if we're going to live there. And that is what our new institute that just got funded is all about. And that's part of what I'm going to talk about, is how we're going to turn those Martian resources into a life support system. So here's the central challenge of life support. Buckminster Fuller said, this is spaceship Earth. We're a recycling, regenerative system hurtling through space. We recycle everything. We have to duplicate all of our functions, but guess what? We don't have oceans. We have a minimal atmosphere. We don't have a living soil. We've got to do that without that. Think of how much our atmosphere buffers things, our ocean, we call our soil the living skin of the Earth. We don't have a living skin on Mars. We'd have to do that with a dead bunch of dust to get this thing started. Here's the central question. Can we make this small and still stable? We can make it small, but one mistake and we're done. So if it's bigger, it's better buffered. So how small can we get it? How efficient can we get this? There's one equation that we're going to use on Mars to make sure this works. And to me as a biologist, this is the most important equation in the world. And I'd invite you to think about, what do you think is the most important equation in the world? Equations are some inputs and some outputs. It occurred to me maybe at universities, we could have an input of students, and on the left-hand side, we could have scientists. And that's our mission, turn students into scientists. But this is an equation, a basic equation that every one of us learned in high school. Now you look at this, and if you've studied this from high school, you remember it, but there's one little hint. That part right there is carbohydrate. So in this equation, we're turning two really low energy inputs, carbon dioxide and water, into two high energy outputs, oxygen and carbohydrate. And this is one of our few equations that's so famous, has a name, photosynthesis. This is so famous that when this runs in the reverse direction, this exact same equation has another name, respiration. So now we get this building block of what can we do with this equation on Mars? Now, what this doesn't tell us is we got to follow the first law of thermodynamics. Energy in equals energy out. So you don't get this without a big energy input. And put that right here. 10 photons to drive this. So I'm going to talk about those 10 photons, but now look at what the inputs are on the Earth. We've got CO2 on the Earth and photons. Let me tell you how hard this is for plants. So I made these beads as a teaching tool. Here's our atmosphere. This is nitrogen. There's 10,000 beads here. 80% nitrogen, 20% oxygen, a little bit of water. This varies, but about 3% water. Where's the CO2? It's a trace gas. 4 black CO2 molecules in our atmosphere. That's what our plants have to work with. Take this trace gas and turn it into a high energy solid. So what do we have on Mars to work with? We have light. Mars gets about 60% of our light, so we get photons are a critical resource on Mars. We have water near the poles, so we get water. How much CO2 do we have to work with on Mars? More than we have on Earth. The Martian atmosphere is 95% CO2. Even though it's a thin atmosphere, it's mostly CO2, so we have more CO2 to work with on Mars than here. So we can run this equation, and we can make carbohydrate, which is the building block of civilization. We make 2x4s out of carbohydrate, and you run it in the reverse direction, we get proteins and oils. So this is the jump start for civilization, and life on Mars is running this reaction with higher plants and with photosynthetic bacteria. Think about Mars. This jar on Mars would be 95 black marbles, and this jar is like 1 nitrogen, and I'm going to come to how important that 1 nitrogen is in a minute. So we got atmosphere on Mars to work with. This equation is written like this in every textbook, and every single high school textbook, and I bet you there's 50 classes on campus where we show this equation and teach students about this. But it always has occurred to me that this doesn't capture the energetics of this, how high energy the outputs are, how low energy the inputs are. It's like we should redraw the textbooks and show it like this. It goes uphill, and the CO2 is a trace little gas, and boom, the output's a high CO2, and then of course we got a lot of photons, and those photons have a lot of energy, so there's our 10 photons. So this is a more schematic diagram of photosynthesis to help people understand the energetics of it. And if you look at this, the CO2 is the output, photons are an input. It's not difficult to calculate the efficiency of this reaction. What's the energy in the output? What's the energy in the inputs? Most people think this is real low, just a couple percent, but the theoretical efficiency of photosynthesis is about 30%. And then when you use 10 photons, you get to 30%. Now, the engineers in NASA go, oh my goodness, 30%. Can't you get better than that? Gee, you should get this thing to 50%. And I've been bugged by this a long time. These engineers keep saying this. And I say, look, here's how to think about photosynthesis. It's about 23 steps, and each one's 95% efficient. 95 to the 23rd power is 30%. There you go. It's a lot of work to get up to carbohydrate. So now think of all these steps. You got anything that's 95% efficient and runs 23 steps in a row? You don't, do you? So there you go. Shut up. So I love this diagram so much. I think here we should propose to put this in all the textbooks and call this the Utah diagram of photosynthesis to help students understand what we're all about in this. So that's theoretical photosynthesis. We still need to get food. And I've spent my career turning photons into food, and that's the core part of what I want to talk about. This is from the movie, a still capture of a little potato plant coming up. It says something about the psychological value of food, which I'm going to touch on in a minute. But how many photons does it take to make food now? Because the first product out of photosynthesis is sugar. It's just sucrose, table sugar. But you can't live on that. You got to have the rest of it. So we have spent many years, all of my students and I, studying this. And we don't just kind of plant seeds and weigh them later. We're measuring photosynthesis and respiration every minute of every day in these chambers. So here's some chambers out in our greenhouse. This is funded by NASA, so the students put a NASA sticker on it. And somebody came to the lab, we give a lot of tours, and they go, oh my, this looks like a bad day in a spaghetti factory. But I'm kind of proud of that. I mean, the plants don't care what direction the tubes go. We're after measuring the plants. So we've not only done it here, we've done it on the space station too. Scott Jones is here, he's worked on this. Gail Bingham's worked on this. We've used this to teach students in high school. It's been a big deal. There's no plants in here, but taken before the doors were closed and the plants went in. But it's been a wonderful thing. It led people to say USU stands for Utah Space University, and we're proud to tout that we have flown more experiments in space than any other university in the world. And you could kind of treat that as a hypothesis, but no one's disproven it, so it stands. So here's what we do. Turning photons into food. First of all, you start with lots of photons, and we have instruments to measure exactly how many photons are going in. Now we bring in a magic green funnel where all this biochemistry happens. What do we get out? 1 gram of biomass. So the question is, how many photons did it take to get a gram of biomass in this system? And after many years of study, we got a number. Now, lots of people from high school chemistry remember this number. It's a guy named Avogadro. I heard that he upgraded to a cell phone, but he kept the same number. So this is 1 mole of photons. What a great ratio, 1 to 1. 1 mole of photons in, 1 gram of biomass out. That's been a particular, I'm pretty proud of developing that ratio, but 1 gram of biomass is only a ½ gram of yield. We have to grow stems and roots and things that aren't edible, so only get a ½ gram of yield out of this. But this is the ratio we're dealing with, and this is how you model life support on Mars. And this only is possible when we have very ideal conditions. In fact, here's the paper that we wrote from this. It's 1988, Exploring the Limits of Crop Productivity. And Plant Physiology is one of our top journals, and this is one of my most highly cited papers. I wrote this with Frank Salisbury, who at the time, it was the author of the best-selling plant physiology textbook ever written. And he's one of the big reasons I came here to work with him. So we've got this moles of photons, but that's not the only thing we need is carbohydrates. We're going to have water. This is another clip from the movie. If you've seen the movie, Mark Watney, the astronaut, has to get water to grow his crops, and he makes his water out of hydrogen and oxygen. He says, I know the recipe for water, and I combine them. And this is how he's got a suit on because it blows up a couple times when he's trying to do it. So how are we going to get water out of this? Now I'm going to show you another clip from the movie, because he scienced the shit out of this. He does the math on how much water he needs, and I'm going to show you a clip from the movie where he does that calculation, and listen closely. It's only 10 seconds long. Listen closely at the end, because he gives a number for water.
Water. I have created 126 square meters of soil, but every cubic meter of soil requires 40 liters of water to be farmed.
Did you get that? 40 liters of water per cubic meter to be farmland. 40 liters. He did the math. Now I get to show you something. This is Martian lunar simulant, which we get from NASA, and we can grow plants in it and do lots of tests on it. And This would be an enormous deal if it was from Mars, but it's not. It's from a volcano in Hawaii, and it was selected for characteristics like Mars. So let's do the math. Oh, I've got to show you my slide here. There. 40 liters of water is 4 mils in 100 cubic centimeters. So here's 100 cubic centimeters of soil, and I was going to pre-do this, but I think we could have a fancy pipette, but let's see if I can still run one of these. We're going to get 4 mils of water in here. There we go, 4 mils exactly. Now, I'm going to get rid of this so I don't spill it. This is do science right here. This isn't enough water to hydrate this to grow as crops. Let's test the hypothesis. 1 mil, 2 mils, 3 mils, 4 mils. You see that dark band? He has a decimal point error in his calculations. It should be 400 liters of water. And when I read this in the book, I thought, wait a minute, this is not right. So this is a dramatic way to show you that he had a decimal point error, not nearly enough water. But I'm proud to say Mark Watney did not get any of his degrees from Utah State University. Our students wouldn't have made that kind of error. So you need a bunch of water. So how are we going to get this water? So let's model the life support with the inputs and outputs here. There's our equation that we're working with. Now, let's put this right back here. I love the idea that we can take a bubble, and this is a great thing to do for students, take a bubble and launch it into space. I showed this in my TED Talk a few years ago. You put a rocket under this. So what a great thing for students to calculate in classes, because you're going to launch your house. How much yard do you have to take with you to sustain yourself? How big of an area of yard? So let's look at this. Here's the bubble. Here's the house. We got people exhaling CO2. But our noble plants come in and turn that CO2 back into oxygen. And if we grow all of our own food, the stoichiometry of that photosynthetic equation at the top tells us we're going to have just the right amount of oxygen. We can keep this in perfect balance if we're growing our own food. Now, if we start to use food to make 2x4s, to build houses, not food, carbohydrates, now we're going to have extra oxygen. And that's a great thing to have on Mars, is lots of extra oxygen. So we run this to get the oxygen. Here's the bigger challenge. We got a lot of waste to deal with, and this has to be the most perfect recycling program ever. We've got to recycle every speck of stuff. We put that back in the plants, and they give us purified water. How much water are we going to get? If we grow all of our own food, this is not a hard math thing to do, 200 liters a day. The plants make way more water than we need. You could wash and wax your rocket ship every day with that kind of water. It's an enormous amount of water. But we have to recycle it. It's a finite resource. Now, the plants are not going to do that waste recycling by themselves. They're going to have microbes, and they're going to have some surfaces to grow on, so the lunar soil is going to help us recycle the waste, along with the plants and the microbes. But that waste recycling is every bit as big a challenge as it is to get the oxygen. Soil. I'm in the plants and soils and climate department, and it's a great honor to work with all these great soil scientists. Here's Mark Watney digging up Martian soil to bring inside his habitat to grow his food. How's that going to work? By the way, soil generally means something living, And so it's a big controversy if we should ever say Martian soil, because it's dead. But we still call it soil anyway. So what are we going to get out of that soil? If we can recycle things in 100 days, this is a tall challenge, this is how much of the elements we need to bring with us to get the system started. Bring from Earth. We're not expecting to get phosphorus, potassium, calcium. The micronutrients are all tiny from Mars. This is what we're going to bring us from Earth. So that's okay, that's doable, 4.3 kilograms, but it's still a lot of weight. It's just an enormous amount of weight, and that's assuming we can redo it in 100 days. That's a really ambitious. Might take 1,000 days to recycle everything. But there's one element on here that's already on Mars, nitrogen. Remember that one bead of nitrogen gas that's in the atmosphere? I'm going to show you another equation. This might be the second most important equation in the world. In fact, multiple Nobel Prizes have been given for this equation. This equation also has a name, nitrogen fixation. Turning the low energy N2 gas in the air into fertilizer and ammonia. And this is so famous that this great book got written about it, The Alchemy of Air, one of my favorite books about the two German chemists that first worked this out, really brilliant chemists, to be able to do this. Well, guess what? There's light on Mars, there's nitrogen on Mars. Can we do this on Mars? What happens with the energy? Lots of photons, huge. This happens on Earth, free living bacteria. But the beauty of doing this with the civilization was at the brink until we figured out how to do this with fossil fuels. Huge amount of fossil fuels to fix atmospheric nitrogen into fertilizer. It also makes bombs too, but into this high energy compound. And part of the reason this is so tough, nitrogen's a triple bond. It's really hard to break that bond. So where do you think NASA went to find the expertise to run this equation that came here? Lance Seefeldt and I are working together on this project, and this is Lance Seefeldt's career's work. Led to the Wynne Thorne Award maybe 5 years ago. This is not a trivial thing, but if we can do this on Mars, it's a breakthrough. It's an enormous breakthrough. So look at this. Low energy gas, high energy solid. This equation doesn't quite capture the energetics, so we ought to show this like this, and the textbooks ought to be rewritten, and we're going to call this the Utah diagram. It's a whole bunch of steps to get up to the nitrogen in this. So we're almost at the end of what we can do. Mark Watney had to get enough light. In his habitat, had been sealed so we didn't get cosmic radiation. He magically got this light to grow the plants. But how much light did he need, and where are we going to get it on Mars? Here's an artist's conception of what Mars looks like. Beautiful greenhouses. Wow, who wouldn't want to go to live in Mars like that? It's wonderful. See those rocks? Those are all meteorites. There's no atmosphere. The meteorite's going to hit that glass. You think that's going to last long? Forget it. And you think, how are we going to make that so it filters the cosmic radiation? That you can't. We don't know how to do this. So our plants on Mars are going to be inside. They're going to be underground to protect from radiation. How are we going to get the light to them on Mars? Up till now, we have used photovoltaics and electric lights. Photovoltaics are about 20% efficient. The ones on the space station are 15% efficient. Our best electric lights, LEDs, we've got them up to 50% efficient. Great. Well, 20% times 50% is 10% system efficiency. Now tell those people that photosynthesis isn't so good. Their electric lights are 10%. But for this new NASA proposal, we're partnering with a company in California to do fiber optics, concentrating mirrors in fiber optics. those are already 30–40% efficient. We think we can get them to 70% efficient. So that's some of the cutting edge of where we're headed with doing this. And with that, with a football field size of these concentrating mirrors, we calculate we could feed 25 people. So this is doable for getting the light to the plants underground. There's one final frontier that we have also worked on at Utah State University, and this one is more difficult. It's in the movie. Mark Watney gets very bonded with his plants. Psychological. Scott Bates has had funding with us to do, he's from the psychology department, to do psychological aspects of this. This is hard to study, but all of the astronauts that come back tell us stories about how they got bonded with their plants up there. And the most famous story that I love to tell is a Russian physicist that was told he had to work on his little mung bean germinating seeds, and he says, I don't like biology, I'm not doing that. And they say, you have to do it, it's part of your job. He got up there and he measured them, took measurements. He was there a year, and towards the end of that year, they'd say, quit measuring the plants so much, get back to work. He came down to Earth, he had a press conference, and he said, long-term space flight without plants is impossible. And that's been a great line for us to say this is a big deal. So I'm going to end on this one slide here. This is a view of the night sky from Mars. You know how you go out at night and you can see Mars? It's just barely, if the light's just right. So see that speck? It's a speck up in the upper right-hand corner. That's the Earth. Imagine being there and your home planet's that far away. This is a big frontier for us, and we're excited to see where we can get with this. And thank you for coming. I'm happy to share this stuff with you.